Good.
Okay. Nice and small crowd, but that's kind of.
Kenneth, are you not introducing him? You're supposed to do that.
I don't introduce the last guys. Okay. Welcome. This is Bryce. He's going to be talking about introduction to category theory, a very underappreciated field of mathematics. Enjoy. Yes. So, as my friend here was alluding to, many of us are quite familiar with subjects like set theory, which we might not necessarily study ourselves, but which we use very frequently when we're studying other subjects because we need access to sets for defining. Category theory turns out to occupy a very similar role in mathematics to set theory. You could go and study categories in their own right, and many do, and they end up speaking this very strange language that the rest of us can't understand.
Yes.
Like most of us don't study set theory, and yet we still use sets. We still benefit from having sets in our repertoire. Most of us, while we're not interested in categories themselves, would benefit from having a little bit of understanding of category theory and just to know when it's popping up in our work and when maybe we could be using some theorems to simplify. Because that's mostly its purpose, in my perspective, to be at to simplify stuff otherwise. So let me first ask everybody in this room, has everybody seen like groups before? Perfect. Okay. So my two examples of what categories are before I go ahead and write down the definition and dispel all the mysteries is the set of all sets, the class of all sets, together with all of the functions between sets, and the set of all groups, together with all of the group homomorphisms between. So what are some things that these structures have in common? Well, they have collections of objects, either sets or groups, and they have collections of arrows, things that point from one object to another. Now, if I have an arrow that goes from one object to a second, the second arrow that goes from the second object to a third, then another thing that I can do in both the category of sets and in the category of groups is I can compose these arrows. I can take two functions or two homomorphisms, and I can compose them. You'll notice here, the composition happens in reverse order to the order that arrows happen. So that's a little confusing, and it's something you have to remember when you're writing down composition of functions, and either in the form of a diagram or in the form of a little circuit. So this is the sort of basic thing that any category is going to have. It's going to have a collection of objects, a collection of arrows, and a way for us to compose these arrows together. There's going to be a couple of extra technical requirements, but that's essentially all there is to it. So because there is so few requirements on what it takes to be a category, lots of things wind up being categories. Categories can look lots of many different ways. So I'll give some different examples besides just the category of groups and sets. I'll give one other. But right now, let me actually write down the definition. You guys can think what you think. Okay. The category is actually a couple of different things. It comes with lots of different pieces of data. It's an object class. So I use the word class here deliberately because sometimes the collection of all of the objects in our categories does not form a set because there's too many damn things. Sets aren't big enough sometimes. And the easiest example, the one that's closest to the ground to pick up, is the set of all sets. It doesn't exist. Run into Russell's paradox. To deal with this, we invent one level of data structure higher, the class, and we just stuff all the sets in there. So yeah, we've got classes you could go and make higher data structures that classes live inside of. We don't need to do that because. So that's why I mentioned classes. But yeah, a large category is one where this object class is actually a class and not a set. A small category is one where this object class is a set.
So I have a question about classes. How technical is the definition, like explicit definition of a class?
It's literally just you introduce a new primitive notion, or rather a different primitive notion. So if you want to know more about it, look up NVG, Neumann, Bernays, Gödel, that theory actions. It's a conservative extension of ZFC. And by conservative, I mean all of the things that are true in ZFC are still true in NVG. And if you prove it in NVG using only ZFC rules, then it was true in ZFC to begin with. So the only things that it adds into ZFC are class. And so the only time you're proving anything new that isn't ZFC related is when you mention the word class.
So people working in category theory, they never really considered the underlying class of objects in their category.
I mean,
as a like data structure, they don't.
No, exactly. I needed this word in order to avoid logical paradoxes.
Technicalities.
Exactly. I need some way to do it rigorously, but I'm not going to spend a whole lot of time.
Okay, that's fine.
Yeah. But yeah, and that is the perspective.
No, because
the same kind of weird, like we're just like. It seems a little unsatisfying to be like, well, in order to run away from Russell's paradox, we're just going to invent an entire new tier of data structure. Yeah, but it is something we can do, right?
Yeah, so I mean, it's just every category theory textbook opens with set is not general enough. We need class, and then they sweep.
If you want to know more specifically about the actual underlying set theory stuff, look at NVG.
Yeah. But at that point, just set theory stuff, or even worse than set theory.
So anyway, an object class, which once again, the class is just like a set in the sense that it contains other stuff. It just might be bigger. So an object class, and for all pairs. Y. A class. Y. These are going to be the morphisms in my category C from X to Y. So we're in the category of sets, and X and Y are sets of mine. Then this would be set X, Y, and it would be the category. It would be the set of all set functions from X to Y. And I mentioned that this is a class, but in the category of sets, I just called it a set a second ago. And I wasn't lying. It actually, given a pair of sets, set of functions between them is also a set. And when that happens, when it's the case that a category has all of the morphism classes between objects actually being a set, we call that a locally small set. Small is when the entire object class is small. This guy being small. Okay. Or this guy being a set. And we're all triples. X, Y, and Z, an operation composition that I mentioned a minute ago. This is how I wrote product of sets. I'll talk about products later, and you'll even see why I do it that way. So, an operation, composition, and all of these guys together have to satisfy some rules. Here are the rules. All X in my object class. We've got an identity morphism, I to X, in the set of all the class of all morphisms from X to X. And he does what you think he does. That's right. Yeah. So I X is equal to F. I X compose G. For all F. He does what an identity. Okay. Maybe substantially short. This is and this just basically means that if I have three morphisms, this O, that is not O, that is that composition right there. But if I have three morphisms, yeah, three morphisms. Fine. I have three morphisms, all composable in a line like this. Associativity is the statement that there is precisely one morphism that I can form by composing these guys all together. It's not the case that if I compose this guy first and then that guy afterwards, that I get something different from composing these two and then that guy. And that's it. That's all in general a category needs to have. I need to have this ability to operate on composable pairs of sets of morphisms. And this operation of composition needs to be associative. And everything needs to have an identity. But that's all it takes to be each category. Yep.
No.
Okay, and like I said, the category of sets and the category of groups both satisfy this definition. So in the case of sets, the object class is the class of all sets. For any pair of sets, it's going to be the set of functions between them. Composition is exactly the function composition you use. The category of groups. Object is now the set of all groups. Object, small category. And now instead of the set of all set functions between our groups, it's going to be the set of all group homomorphisms. Composition functions, still composition. And you might, from my two examples, think to yourself that, oh, okay, what categories are things like the sets and functions plus extra structure on top of it and functions that preserve them. And that's not actually what categories are in general. Categories can be those things. They can be some set plus extra structure together with functions that preserve that structure. But they can also be very different sorts of things. So as an example, does everybody know what a partially ordered set is? Let me give you a scratch try this. So X less than or equal to, or greater than or equal to the way I wrote it, is a partially ordered set. Yeah, so this is going to be a partial order, meaning one of the things that's true about a total order is that any two elements are comparable, but that's not necessarily going to be the case here. So you won't see in the requirements that any two things are comparable somehow. One. Little x is less than or equal to little x for all little x in big X. So everything is less than or equal to itself, what we call reflective. Less than or equal to y and y saying less than or equal to. That's actually greater than or equal to. And I can imply y is equal to x. So if x is less than or equal to y and y is less than or equal to x, then they have to be the same thing. This is called anti-symmetry. And a lot of students trying to do it. Right. Greater than or equal to y. Applies. But this is the definition of a partial order. So it's very much like total orders. It's just we've excluded the fact that we require any two elements in the set need to be compared. But the more important thing to mention here is that I can actually interpret every single partially ordered set as a category. And here's how I do that. If objects are going to be the points in the set, those are going to be my objects. And now, I will say that there is a morphism from y to x if x is greater than or equal to y. There will be one unique morphism instead of morphisms from x to y. And otherwise, there will be nothing. And it turns out that will be the category. You'll be able to compose things. Everything will work out just fine. Everything will have the identity because something is comparable to itself. You want unique morphism in its identity. And now, in this situation, you have to accept that categories don't have to look like objects which are structured sets together with morphisms that are structured functions, because now our objects are points in a set. They don't have anything in them at all, right? Nothing to it. The morphisms, they're just whether or not one of these relations is true or not, right? But you have to point through that. We'll have a hard time doing it. It's not much of a function anymore. So yeah, things in categories do not have to be sets and functions. They can be very abstract. That is the first thing to get out of the way. They don't objects in categories don't have to have points. Morphisms between categories don't have to be functions that send points from one to points in the other. And that means that the sorts of things that you can define inside of the category are related to the stuff that you can define in that theory and other disciplines. But they differ in the flavor that because we don't in general have access to elements.
Wait, sorry. I don't think I digested your example. So if I take x to be the real line, right?
Yes.
And I take the partial order to be just regular inequality.
Normal order.
So then the points are.
There's going to be a unique morphism from x to y if x is less than or equal to y.
So my objects are the numbers or they're not?
Just the exactly, just the numbers, just the points on the.
Okay. And you're saying that if I have, say, for example, 5 is less than 0, right? There's a morphism from.
5 is not less than 0.
Sorry, 5 is greater than or equal to 0.
There is no morphism from 5.
Okay.
But 0 is less than 5, so there is some morphism.
Okay.
And yeah, it's kind of hard and abstract because well, now I have literally no sense of what those morphisms are. Yeah, no, because they're not really anything anymore, right? They're just whether or not a relation is true. There's not really substance to them. Answer to them. And don't worry if that sounds weird, scary, or makes you want to fall asleep. Category theory has this strange way of slowly stealing your motivation to study it as you're looking at it, even if you know already why it is you're interested in seeing it. So don't be worried. That's not some problem with you. That's natural. That's how it works. That's how it's something that we all have to overcome together. But anyway, like I was saying.
No, I'm still. So okay, what are the axioms that a morphism has to satisfy?
Morphism doesn't have to satisfy any axioms. This is something that belongs to the set. It's the set of arrows from x to y.
And what do the set of arrows do? Because I'm still kind of confused.
They're just they don't have any properties in themselves.
Transitive properties.
That's the only property you need to satisfy. And I guess, yeah, and it does. Yeah.
Literally the only thing that's set.
Okay, I get it. Thank you.
Okay. So yeah, so composition is all we have access to. We don't have access to So the definitions for things that we end up writing down are going to be written down in terms of composition, not in terms of elements. So what are some of the most important things that we end up studying in set theory? Things that we end up using in like literally every other thing we do. Perfect. Specific types of functions. Not in set theory, but
Projections.
oh, like I like exactly. Anything like bijection and injection, a surjection, these guys are super important in all areas of mathematics, right? Whether you're going to study set theory forever, or if you're going off to study one of the other subjects.
Or you're counting, even counting.
Exactly, yeah. It's going to show up. There's no way to avoid injections and surjections.
Sorry.
And so you might ask yourself, since we have morphisms, right? We have arrows that go from one thing to the other. And in a way, morphisms are generalizing functions on sets. You might ask yourself, all right, well, when can a morphism be injective or surjective? We have to figure out a way to pose injectivity and surjectivity in terms of composition. There's a way. So, definition of monomorphism. Dimorphism in a category is called a monomorphism. If for all F and G, all morphisms, I'll ignore that for the moment. I'll just leave it implied. M composed with F is equal to M composed with G implies F. So we say that it's left-handed. If I have an equation with M on the left, I cancel that guy off, just like he was a number that I would divide. Okay, so where the hell does this come from injectivity? How the hell do we go from injectivity? Well, let's assume for a moment that F and G were functions that M is injective. Okay, well, then if when I send a point F through G and F, M then sends the output to the same point. Well, because every fiber of M contains precisely one point, that means that the point that F and G map X to had to be the same in M zone. So that's when we're looking at functions, injective functions have this property. And when we step up into categories, since we can't talk about elements anymore, but we can still talk about compositions, we can now pose the same property injected in this way. And you notice that this is not this is not the only way that we could have characterized injectivity per step. This is not the only property that we could have written down as having generalized injectivity. Anybody have any other idea, another way that you can define an injective function in sets, just using composition, using the existence of morphisms and composition? Sorry, this sounds a little. How about the existence of a left inverse? Yeah,
It does, yeah.
the existence of a left, if we had a left inverse, right? So let's say that M had a left inverse. If M has a left inverse, then what can I do?
Decompose with
Suppose I'm left with the empty. I'll call it L. I'm lacking in creativity. Okay, and then since it's an inverse, this just has to give me the identity. Goes with F equals the identity composed with G, and from there it's out. So something that is left invertible has this property already. It's something that's left invertible is stronger than a monomorphism it turns out that you can already prove plenty of stuff with just this monomorphism property. So in general, in an abstract category, being a monomorphism is not as strong as being less invertible. So we can go back this way. We can show that something is less invertible and show that that makes it a monomorphism. But it's not generally the case that something that's a monomorphism is going to be. Examples, I'm called. But take any injective continuous function that is not embedding, and this happens all the time. So that's the easiest.
So essentially, it is injective but not surjective.
So more specifically, it's the problem is that you need to not be able to go. Well, I guess in topology, anything. Because the way I've written it down, I'm not allowed to co-restrict first. So it's not. It wouldn't just be a continuous injection that doesn't have that isn't an embedding. Here, it technically would be something that could potentially be an embedding, but it's not embedding onto a retraction of the underlying code. I might have fixed it a little bit more. Sorry. But the idea is that sets and functions between sets have very little structure. So it's very easy for lots of things, lots of concepts to sort of end up being precisely the same on them. But in more general categories where objects have more structure and so constructions on them are more likely to fail, properties like these wind up not necessarily being nice. But this is the idea behind properties in categories. The way we end up defining them is using composition as opposed to anything else, because that's literally all we have access. So we have a dual. I haven't mentioned anything about duality yet, but we have a dual notion to monomorphism called method, which, as you can imagine, is basically it does practically the same thing. So I would say that E is NFE. Yes. And so now instead of using what cancellation, we just use right. So F composed with E equals E composed with E implies F equals. And the exact same argument that I made there before, something that is right invertible will be an epimorphism in general, but epimorphisms don't necessarily coincide with the collection of right invertible. Okay. Now, there's probably, now that I've mentioned epimorphisms and monomorphisms, I think someone had already mentioned isomorphisms. I think someone had said the word earlier. And if you had, you said it? Yeah. Good on you. That's probably one of the most important things to talk about in category because.
So wait, before you raise that.
Yeah.
So does definition epimorphism imply that it's right invertible?
No, it doesn't.
It doesn't necessarily need to be right.
No, exactly. It doesn't need to be right invertible. A right invertible thing will be epimorphism, always,
Yeah. Okay.
but not necessarily.
Okay. And same thing with monomorphism, right?
Being mono and being epic.
Yeah.
They are, in general, not the same thing as being invertible. And that's left or right. And it probably goes without saying, but if you are left invertible and right invertible, then you're just straight up invertible. Just like if you were, you were in algebra and you had something that was a homomorphism that was left invertible and right invertible.
Isomorphism.
Very quickly be able to show that it was full-on invertible, and the same is true in general. Okay, but I think I'll mention them briefly, but I want to get to talking about functors, and then with how much time that I've got left.
It is 2:30.
I'm going to try to talk about products. I'm not going to be able to talk about units in general, but I want to get to if you guys roughly inoculated with the idea of what limits and categories are by looking at the most prominent example when you all will see all the time. They're products. You see them everywhere. Topological spaces and in groups you'll see product groups and product spaces. But before we move on to talking about functors, just a brief word on isomorphisms. Isomorphisms are the eyes through which we mathematicians see objects in particular. That's sort of the raison d'etre that's behind jokes that you might have heard where topologists can't tell the difference between copy and stones. The idea is that to a mathematician studying objects inside of a particular category, any two objects are indistinguishable from each other if they're isomorphic. And that literally means for you that, yeah, they are the same thing. More than being the same thing, it's kind of just like you're seeing a representation of the bigger, larger thing that those things actually represent. So, isomorphisms are important because they are exactly what determine the equivalence classes that correspond to the actual things that you're studying. So if we're looking at topological spaces, well, I define a topological space to be a set together with a topology. But what we all actually know is I don't really care about that set and that collection of its subsets. What I really care about is the homeomorphism class of all topological spaces, all of those sets together with their subsets. That's homeomorphic for that guy. I just need to, I need the representation first before I can talk about the second thing second. But isomorphisms give us precisely that language to go, oh, but this is the thing that I really care about, the actual topological space, the actual one, the homeomorphism class, and not the representative that I did. Okay.
What year are you, just to make sure? What year student are you? Okay, so so have you taken algebra or anything like that? Algebra topology?
Not.
Got it. I'm just making sure. So in case you're struggling to figure out what terms, it's just
Yeah, I mean, it's a very intimate thing, so don't be afraid to interrupt. Okay, so functions. We've seen already when we're talking about sets that we have functions between them, ways of mapping from one set to another. And in category theory, we have objects and morphisms, ways of going from one object to another. You might think that maybe somehow, perhaps there's a way of going from one category to another, and you wouldn't be wrong. You would be exactly correct. So, functors, I believe is something that is stolen from actual analytical logic. Like if you go and study logic in philosophy, they use the word functor for something completely different. I have no idea what it is, but so
As usual.
yeah. So a functor. So given two categories. Prime F and C prime is a functor if, and so I write it like this, but it's actually got a couple of different pieces. So it's got an object part. So part that has the object class. The first category. With minus that I do. Until I die, I'm just going to be smudging up words everywhere. We have match objects to objects, and then for all objects in C, I forgot to mention this earlier, but in general, instead of writing objc, we'll just write xy in C, and that means the same thing. It's in the object class. I don't want to write more stuff, and that's also how it will be in literature as you go. Yeah. So I'll never do that for morphisms, though. I'll always tell you that a morphism belongs to the set C for X. I'll always specify that. So for all of you guys, y So we'll have, in addition to this object part, for every pair of objects, a morphism part, which sends morphisms in the collection of morphisms from X to Y to morphisms in the collection from the output of F of X to the output of F of Y in our case. So we have these two maps, and we're going to have it satisfy two properties. So a functor has to preserve composition. It's like the only structure that a category has. So a map between two of these things is better to preserve. It's the only thing they can do. In addition to preserving composition, it also preserves the identity. Any identity map on any space X, F of the identity of X, always just. And you'll notice already that I have dropped writing these because nobody will ever write these, and I'll never write these. I emphasize that they're technically different functions. There's preserves compositions, preserves type. And these are the relevant sorts of functions between categories. And already with just these two properties alone, they're actually doing something pretty strong for us. Anybody ever heard of an invariant? You know what an invariant is? Go ahead and hit me with whatever definition you got. So here, when we talk about how we're transferring between two systems, we specifically have a word for that in categories. It's isomorphism. So an invariant for us is something that's preserved as we go from one object to another by an isomorphism. And it turns out every functor is an invariant. Every single functor. If you give me a category and define a functor from that category into another, you have an invariant now on all the objects in your first. What do I mean by that? Any functor will send two isomorphic objects to isomorphic objects. Functors preserve isomorphism. As a result, they are invariant. So one very naive, easy way to go off and build invariants is to build a functor. But just a functor alone, while it is an invariant, it might not necessarily be a nice and strong invariant. So you might need to necessarily do more work. But technically, every single functor is an invariant. So let's talk about it. This is one argument. Give a couple different phrases. Start with something simple. We've all seen groups before. We know that every group has a commutator. So we can send every single group to its abelianization. Abelian groups. And yet, all it does is it just takes a group and quotients it out by its commutator. And it associates any homomorphism between two groups, the induced homomorphism between their abelianizations. This will always work out. It doesn't take very long. Okay. So, and very critically, if a group was already abelian to begin with, what is its commutator?
Trivial.
It's trivial. It's the identity. So I'm quotienting out by the identity. I'm not doing anything. So if I have two abelian groups and I ask about morphisms between them, this functor does nothing. It just passes them right on. This is a special kind of functor. It's what we call fully faithful. Well, actually, this functor, excuse me, this is the other way around. This functor is what we call full. So every single group homomorphism between abelian groups arises as the image of a map of a homomorphism between groups, and that's kind of obvious because it doesn't take too much work. But if you have a group, but I don't want to get down to the group theory right now. Feel free to go ahead and look at that as an exercise. But this is a full. But on the other hand,
So wait, so sorry again. What's the definition of full functor?
yes, I'm about to write those down.
Okay,
So
go ahead.
I'm just bringing up that there are a couple. So the other thing that I can do. So I'll give it the name line. We go right the other way. I'm going to send every abelian group back into the category of groups, and how I'm going to do it is just leave it alone. This one's also full, but this one's now faithful in the sense that it will never send any two morphisms from the same morphism set to each other. I'm going to mention what all these words here in a moment. But you
So
there are
faithful
other
means,
properties that functors
the morally faithful means for functor that it's
got something to do with injective.
it's injective on the morphisms and the
Individual
objects,
morphisms.
and then the objects as well. Not necessarily. Okay.
Individual morphisms. I'll write that down here in a second.
Okay.
But yeah, there are functors out there, and the properties that functors have between different categories give you information about the objects in those underlying. So let me go ahead, since we're kind of spilling the beans. I got spoiled here. Why don't I just go ahead and write down what full and faithful mean?
Go
And
ahead.
I'll talk about some of the properties of full and faithful functors with respect to monomorphisms and epimorphisms. All right. So full. Skip down on me getting to show you guys a sheaf. Sheaves are functors. If you've ever heard the word sheaf before and you're like, what the hell? It's a type of functor. Okay. So full functor. F to C prime. Instead to be full, it is a large lunch. So now it's going to be for all pairs y in the domain category. Morphism part that maps this morphism set. This one. That is a surjective map. Every pair of objects. So notice here, I'm not saying anything about the object map. And I'm not saying anything about the set of all morphisms in either category. There might be morphisms in C prime that F never hits. Okay? It's for every pair of objects, this guy is mapped surjectively onto this guy. That's it. That's all fullness is referred to. And faithful, all it would take for me to say faithful. So, in faithful, is injected. I even write surjective. That is correct. Full if that is. Okay. And these are the morphisms between objects express how those objects are related. They are the structure of the category. So functors that preserve that structure first are sort of, that's the first most important thing to care about before you ever start talking about objects. You want to care about what functors are doing to morphisms. And once you know that a functor is both full and faithful, fully faithful, as we call it in business, then it turns out that every single one of the underlying groupoids formed by composition in your category, these things are mapped isomorphically to each other by a fully faithful map, because composition is already preserved, and the thing's going to be a bijection on all the associated elements. So, fully faithful functors are very powerful because they preserve lots of structure about the underlying morphisms, and the structure of the underlying morphisms has a lot to do with the structure of the underlying category. Morphisms between objects tell you how those objects are. So functors that preserve those relations preserve lots of structure in the category. So there's some other things that functors that have to do. So for instance, a fully faithful functor, I haven't mentioned what a universal property is, but a universal property is any property that you can give to an object in a category that defines it as isomorphism. That is to say, if two objects in a category have this property, they have to be isomorphic. A fully faithful functor will preserve universal properties. So if an object has a universal property, something stated in terms of morphisms having particular properties in one category, and is matched by a fully faithful functor into another category, will satisfy the exact same universal property. And just full and just faithful alone won't do nearly as nice things, but there are still some nice things that can be done. Faithful functors in particular, they do what's called reflecting epimorphisms and monomorphisms, and that doesn't mean that they preserve them. It doesn't mean that they'll send a monomorphism to another monomorphism or an epimorphism to another morphism. It kind of means the reverse. It means that if you landed on an epimorphism, you were an epimorphism to begin with. Or if you landed on a monomorphism, you were a monomorphism. And these are all really basic facts. You can prove them to yourself really quickly just from the definition of faithful. I would highly encourage you to do so. Like, take your time. Okay. So, full and faithful functors. And before I move on to trying to talk about product, I'm trying to speed up. I really wanted to there are a bunch of really important basic ideas in category theory that show up all over the place.
So maybe could we talk about the reason to enter? Why spend the time learning category theory?
So category theory kind of is like grammar to set theory's vocabulary. It just gives you more of an ability to phrase complicated ideas in language.
Sure.
That's essentially it. To say nothing of the fact that it allows you to have different areas of mathematics talk to each other. So for instance, as someone who does lots of topology, the main value to someone doing topology in category theory is that we translate our problems in topology into algebraic problems. And this is something that we literally couldn't do without category theory because it is via functors, by a category, taking maps that take things in topological categories to things in algebraic categories that we achieve this. So it's not simply the case that you need to do this if you're having two areas of mathematics talk to each other. Lots of the deeper ideas in modern mathematics have either been, they were either derived using categorical reasoning, or they can be made more powerful by putting them into the categorical system. Because it's not like it's sort of like taking linear algebra and then putting it into modern vector notation versus like really old index notation. It's still the same subject, but one is much easier to comprehend because it's much shorter, essentially. It's been simplified. And that's, in my opinion, what category theory is. You can talk about all the exact same things and get to all the exact same places without it, but once you know all these things, it gives you a short. It's just you have to know all.
So maybe this is asking for too much, but could you give an example of a classical theorem that has a categorical analog, which people Or well known, it's well known.
So
It may be too much to ask.
yeah, no, I guess it depends on what you mean by categorical.
Well, you mentioned that like there's some,
So, okay, so here's what I'll give as my example. So there's something called the splitting lemma.
okay,
And
and
it's a
homological algebra?
Yeah,
Yeah.
exactly. It's a result in homological algebra.
Okay.
It turns out that there's lots of why don't we go ahead and write it? Answer your question. Okay. So this is an exact sequence, meaning that the image of every single one of these morphisms is exactly. The image of every single one of these morphisms is the kernel of the following corresponding morphism in the composition. And the splitting lemma is the following, that the following three things are equivalent. I not convertible. Sometimes you'll hear it said that it has a retraction to the right convertible. Sometimes it'll be said that it has a fraction. Two, D is isomorphic to a byproduct. Splitting lemma, and this is a statement, you could prove it in the category of commutative rings, or the category of moving groups, or the category of modules over commutative rings. You could do it in all of them if you wanted to. Or you could just do it in the setting of abelian categories. And then once you've proven that any one of those other categories is abelian, then you automatically get this and many other theorems in homological algebra for free. So this is the value of category theory. Say I wanted to use some category out there as my homology object for studying something that I'm studying. Well, I could go and prove the splitting lemma and all of the other results of homological algebra in my new setting that I just discovered, which would be a pain in the ass. Or I could just go prove that it's an abelian category and then take advantage of all the stuff that's been proved for free. Right? Instead of having to prove it a million times, every new example, I prove it once in high generality, and then I can go back for every single specific example that I'm interested in, and then just use all the stuff that's heard. That's in my opinion, and this is not unique to category theory in any way. This is sort of the story of mathematics, right? Like finding more general statements that clear up a whole lot of our work instead of having to boil down each and every single individual special case. Because we can do that, and I'm sure it'll make a lot of work and a lot of papers. But if we want to get to the actual answer, there's a faster way to do it. Anyway, so hopefully I have enough time here to at least briefly mention. I have 5 minutes. I'm never going to be able to explain how a product.
But it's fine. You have like 3 parts. It's fine.
The more the better.
Maybe even 5.
Oh well. Okay. So yeah, that's where I'll stop right now. We got to do categories and functors, and I got to explain a little bit about some of them.
Okay.
Yeah, so as far as what could possibly be going on next week, I could either go on to originally I was talking with Zach about maybe doing some homological algebra, at least mentioning.
Yes, I actually would really like to see that.
Homological algebra.
Yeah.
Okay. Yeah. So yeah, that was either going to be that, or I could have talked about. I think that's probably relevant to everybody's interest.
So, any last questions before I stop recording?
Yeah. Before I go.
Yeah, I had a question. So whenever you define a function, you're essentially defining two.
Exactly. Well, you're defining one function between objects, and then you're defining another function for every pair of objects.
Right.
So infinitely many potential.
Right. So yeah, so the definitions are kind of independent for the most part with each other. So
Yes, exactly.
Okay, so when you talk about a fully faithful function, functor, so it seems like the definition relied heavily on the function that takes pairs of domain objects, I think you called it, in the category, right? The second function. So can you, I guess my question, I think maybe we already answered it, but it's can you have a functor that's fully faithful, and the first function that you define, does it matter too much what the first function?
No, yeah, that's a great question. Actually. Yeah. So I can have the object function, the object part of fully faithful functor, be not injective and not surjective. However, there is a limit to how not injective it can be. So it turns out that by making a functor fully faithful, it becomes injective up to isomorphism. So if two things got mapped to isomorphic things, in the end, they had to be isomorphic. But it's not necessarily true for full equality. So it satisfies an injectivity requirement, but not the fully strong injectivity requirement. Object part becomes invertible up to isomorphic, or injective up to isomorphic. And there's a corresponding notion of surjective up to isomorphism. Well, it turns out that when you are injective up to isomorphism, surjective up to isomorphism, and fully faithful, you are what we call an equivalent of category. So all the properties of the first category will be exactly the same in the second category. Something that's essentially surjective and essentially injective and full.
Any more questions? All right, thank you for the presentation. So like you said, it's going to be a multi-parter, so stay tuned for part 2, part 3, however.